We're now going to turn to our next speaker, who will be Jordan Ellenberg. Jordan Ellenberg is the John D. MacArthur Professor of Mathematics at the University of Wisconsin-Madison. Ellenberg was a child prodigy in mathematics, and he obtained undergraduate and graduate degrees at Harvard before beginning teaching at the University of Wisconsin-Madison. In 2012, he became a fellow of the American Mathematical Society. He was named a Guggenheim Fellow in 2015, and he was also elected as one of 6 A.D. White professors at large at Cornell in 2019. His research focuses on the fields of number theory and algebraic topology, the study of abstract high-dimensional shapes and relations between them. Now, if you look at the biography that's associated with this program, you will see far more than just number theory and algebraic topology. It's a list of several detailed mathematical topics on which Professor Ellenberg focuses. I have to admit that I, and possibly some of you, have no good understanding of most of those topics. But Professor Ellenberg also writes for popular audiences, and he's had articles in the New York Times, Washington Post, Boston Globe, among others. His latest book, Shape, The Hidden Geometry of Absolutely Everything, is very compelling to read. I just kept on coming back to it, and I suspect that non-scientists and scientists alike would be, this would be the case, and they'd be coming back to it as well. But I'm sure you're going to understand this a lot better after you hear his talk entitled Shape. So let me now just turn the podium over to Professor Ellenberg. Thank you.
Hi, everybody. Well, thank you so much for coming. I decided to change the title of my talk, actually. I think now it's called The Soul of the Fact. And I'm going to try to do like Journey does and Don't Stop Believing, and have like the very last words of the talk be the title. The title won't appear until the very end in true styles. But what I really want to say, my book that I just wrote is about geometry. It's not about the sort of super hardcore, ultra technical geometry that I do as a research mathematician, but about geometry in a much more general sense. And I just want to start by asking, what is it that we're teaching when we teach geometry? Something probably most of you took in school. And, for a long time, for most of the history of public schooling, that meant memorizing and reproducing passages of Euclid, the text. And this was done, I almost feel like it was seen as kind of like a tonic, like a strong drink or an ice cold shower. There's a great passage about math teaching in The Mill on the Floss by George Eliot. I don't know if you remember that there's a geometry section in that book, but there is. And Mr. Stelling, the schoolmaster, is described as follows. They say, Mr. Stelling, who's teaching them Euclid, Mr. Stelling was not the man to enfeeble and emasculate his pupil's mind by simplifying and explaining. So that tells you something about sort of what pedagogy looks like in this time. I mean, he's sort of a satirical figure, but also like fairly typical. Emasculate is an interesting word there, isn't it? That sort of somehow it's a subject for men that is supposed to be bracing and maybe kind of unpleasant. But at the same time as this was a mainstream view about what geometry education should be, not everybody liked it. I mean, we're still in the 19th century in Britain here, and Joseph Sylvester, who is sort of a founding figure of a lot of the kinds of algebra and geometry that we do today, the guy who invented the word matrix, by the way, if you like matrices, that's him. He was very frustrated that the mode of teaching was to recite these ancient texts and not to talk about the sort of developing relationship of geometry with physics and other things in the scientific and physical world. So he said, it is this living interest in the subject which is so wanting in our traditional and medieval modes of teaching. In France, Germany, and Italy, everywhere where I have been on the continent, mind acts direct on mind in a manner unknown to the frozen formality of our academic institutions. So with time, I think people come around to a point of view a little bit more like Sylvester's. coming to America in the 20th century, the Committee of 10, which is a big committee run by Charles Eliot, who was the president of Harvard at the time, trying to rationalize and improve and standardize American high school education. They developed a new vision of what teaching geometry was for, that it was to train students' minds in the habits of deductive reasoning. Not to memorize an ancient text, but to teach students to do something. And this idea has stuck. Actually, this is kind of cool. There was a survey in 1950 where 500 American high school teachers were asked, what is the point of teaching geometry? Why are you doing this? And the most popular answer by far was to develop the habit of clear thinking and precise expression. So again, I mean, this got twice as many votes as the second leading answer, which was to give a knowledge of the facts and principles of geometry. So it's kind of amazing that people are just really out and out saying the point of teaching geometry is not to know geometry. It's to know the kind of mental habits you have to engage in order to understand geometry, not to sort of stuff our students with every known fact about triangles. In this respect, it's sort of reminiscent of another American figure who was a geometry enthusiast, and that's Abraham Lincoln. He, of course, did not have formal schooling, as we know. But there's an amazing interview with him. Admittedly, this interview is recounted by the interviewer, so we can't, it's not his written words, but it's his words as recounted. Lincoln tells the story of being a young lawyer. This is before he's been in Congress and then lost re-election, and he's basically given up on politics, and he's kind of going around the Illinois legal circuit doing cases. And he has kind of a crisis of faith. He's like, everywhere I go, I'm asked to demonstrate this thing was the case. And what does that even mean? So he said, and now I'll quote from Lincoln's words. I said, Lincoln, you can never make a lawyer if you do not understand what demonstrate means. And I left my situation in Springfield, went home to my father's house, and stayed there till I could give any propositions in the 6 books of Euclid at sight. I then found out what demonstrate means and went back to my law studies. And he actually sort of stayed, this wasn't a one-time exercise. He stayed very interesting. And there's a very wonderful anecdote that one of his law partners tells of Lincoln became obsessed with the problem of squaring the circle. Boy, I could give a whole talk about that, but it's a problem, the problem of constructing with only a ruler and compass, these classical tools, a square that has the same area of a given circle on the page. Why do you want to do this? There's a story, we could tell it, but instead, let me just say it became like a figure of difficulty, a famously difficult problem that many people tried and that no one could do, and was eventually actually proven to be impossible, although not by Lincoln's time. It was proved later. So Lincoln becomes obsessed with this, and his partners say, like, we don't understand what's happening. Like, he was working, he just didn't do anything else but this. Like, he stayed up all night. He like had all these like pages and all these different colored inks and his ruler and compass like out on the table. And at some point, he realized he couldn't do it and gave up. And his law partner says, I was very interested to ask him about it, but I could tell it was a sore subject. And so we never brought it up again. What I like about, I think this story actually casts Lincoln in, to me, a very appealing light in that, he had this combination of ambition, the ambition to actually work on this famously hard problem, but also humility, the humility to understand that he had not succeeded, to understand that at least for the time, it was beyond the power to do. He was certainly someone in whom I think it's fair to say that geometry did inculcate positive habits of mind, which went beyond what he may or may not have known about triangles and circles. He had learned what it meant to demonstrate, to prove. So here comes a question then. If geometry is about understanding the habits that allow us to rigorously prove statements, is the point then to automate our reasoning, to make it more mechanical, to make us into deduction machines? Totally no. Sometimes it's been phrased that way, but I think it actually dovetails very nicely with the first talk, this question of like, is the goal to replace the things that humans know how to do with things the machine can do? No, there's a beautiful essay by Henri Poincaré, one of the great geometers of, I guess, not our time anymore, but the early 20th century and late 19th century. One of the main figures in my book because he's so damn quotable, in addition to being such a major figure in the development of the subject. So he writes in 1905, he identifies intuition and logic as the two indispensable pillars of mathematical thought. So he says math is not logic alone. It's two things. He says every mathematician kind of has a lean towards one direction or the other. And the geometers, Poincaré says, are actually the ones who lean towards intuition. But the important thing for Poincaré is that we need both. Nobody's leaning entirely on one pillar. Without logic, we would just not be able to say anything about a geometric figure like, say, like a 1,000-sided polygon. Because you actually can't visualize that. You can't draw a picture of it. You can't really think about it. But you can still reason about it using formal logical tools. On the other hand, without intuition, the subject kind of loses its savor. And then Poincaré explaining this, he launches into a very beautiful extended metaphor, which I'm going to read to you. He says, "You have doubtless seen those delicate assemblages of silicious needles which form the skeleton of certain sponges. When the organic matter has disappeared, there remains only a frail and elegant lacework. True, nothing is there except silica, but what is interesting is the form this silica has taken, and we could not understand it if we did not know the living sponge which has given it precisely this form. Thus it is," here comes the metaphor, "thus it is that the old intuitive notions of our fathers, even when we have abandoned them, still imprint their form upon the logical constructions we have put in their place." So for Poincaré, the proof, the thing we teach our students to do in the 9th grade, is a kind of way of putting a firm skeleton around our thought. And then the goal, difficult as it is to train students to deduce without denying the presence of the intuitive faculty. That's the living spongy tissue, which is where the insight really comes from. Neither can really live without the other. I got to give you one more of Poincaré's epigrams here. There's so many, it was hard to keep myself from quoting them too much in the book, but this is one of my favorites. It's very tangy and paradoxical. He says, "Geometry is the art of reasoning well from badly drawn figures." Right? The figure, the thing that we perceive, doesn't have to be precise. We can still build reason upon it and do a good job. I think Lincoln might have actually said very much the same thing about lawyering. So, I'm going to be brief. There's so much I could say, but let me sort of say one more thing about what's special about geometry. And I want to shine kind of a different light on it than I have been, because I fear that I've been presenting the learning of geometry as a kind of, I don't know, self-help or self-improvement project, like something that's good for you, like your vegetables. And, vegetables are great, but that doesn't quite capture what moves people about it. I feel like I sound a little bit too much like the schoolmaster from The Mill on the Floss, right? He too saw learning geometry as a self-improvement project, but in this kind of very traditional, don't be emasculated, take your cold shower kind of way. But there's sort of a different direction I want to go. And so I'm going to read you a poem, if that's cool. Don't worry, it's not my poem. It's by Rita Dove, who is a former poet laureate of the United States, a professor at the University of Virginia. A wonderful, wonderful poet, and also somebody who has written not one, but 2 poems about math, strangely enough. And I'm going to read you one of them. And it's called Geometry. So here we go. Geometry. I prove a theorem and the house expands. The windows jerk free to hover near the ceiling. The ceiling floats away with a sigh. As the walls clear themselves of everything but transparency, the scent of carnations leaves with them. I am out in the open. And above, the windows have hinged into butterflies, sunlight glinting where they've intersected. They are going to some point, true and unproven. So there's something special about geometry, something that makes it worth writing poems about. My book is actually full of poems. Again, this kind of intersection between geometry and poetry came as a great surprise to me, but you'll find that you almost can't not write about it. Everywhere else in a child's school curriculum, in the end, you have to defer to the teacher's authority or a book's authority, right? When it comes to who fought in the French and Indian Wars, or what are the principal products of Portugal? I mean, and at some point, you're not going to perceive that directly. You're going to have to look it up and take someone else's word for it. Geometry is different. In geometry, you make your own knowledge, and the power is in your hands. And this, of course, is why geometry has often been actually seen as dangerous. It was seen as dangerous by the Jesuits in Italy. There's a wonderful book by Amir Alexander called Infinitesimal about the different trajectories of mathematics in England and Italy, precisely because in Italy, a lot of the new developments, the idea of the infinitesimal, the ideas that sort of underlay, the ideas that preceded the infinitesimal calculus were suppressed. They weren't classical, and so they were suspicious. Even in England, I didn't write this fellow's name down, so I don't have it, but a contemporary of Newton's wrote a book called Geometry, No Friend to Infidelity. Okay, well, you don't have to write that book defending Newton unless there's people out there saying maybe geometry is a friend to infidelity. Maybe this idea that you can figure it out yourself is dangerous because it represents an alternative source of authority. The idea that something like the Pythagorean theorem isn't true because Pythagoras said it was true. It's true because we can ourselves demonstrate, in Lincoln's words, that it's true. That is a feeling of liberation. And I think that's very much the spirit of Dove's poem. I think it's a poem about power and a poem about kind of gathering power to yourself without having to rely on anyone else. But I do want to say, finally, that I've a little bit elided the distinction between geometry and proof. Truth and proof are not the same thing. And we have a habit in math of saying that proofs are what we care about. And it's true. Proofs are something we care about a lot. But we care more about truth. We care more about understanding things. They're highly related, but they're not identical. And that, in some sense, is where Dove comes down. I'm going to read the last line of her poem again. They're going to some point true and unproven. And here, I think, in a way, she echoes Poincaré, that logical deduction alone is not what geometry is about, that the intuition is always there true too. It's the living part of the subject, and that geometry trains us not only to rigorously prove, but also to perceive what we otherwise could not. What happens to Dove in her poem, which recalls a childhood memory. And now we're at the end, and I haven't said the title of the talk yet. As promised, I'm going to leave it to the very last words, and I'm going to leave the last word to the always quotable Henri Poincaré, who actually speaks directly to some of the issues and I would say anxieties that Vijay was raising in his talk. So I'll close with what Poincaré says about the insufficiency of pure logical deduction as a model for what we do when we do geometry. Poincaré writes, "What I have just said is sufficient to show how vain it would be to attempt to replace the mathematician's free initiative by a mechanical process of any kind. In order to obtain a result having any real value, it is not enough to grind out calculations or to have a machine for putting things in order. It is not order only, but unexpected order that has a value. A machine can take hold of the bare fact, but the soul of the fact will always escape it." Okay, so I'll stop there. Thank you guys so much for listening.
Thank you. While I'm waiting for questions, let me just ask this question. You said it's the goal of geometry being demonstrations and proving things rigorously, but isn't that true of all of mathematics? Is there something special in that regard with respect to geometry?
So it's a great question. I focus on geometry for this discussion because for math as taught in school, which for almost everybody except weirdos like me is the totality of your encounter with mathematics, right? Math as taught between the ages of 6 and let's say 19 or 20. It is in the geometry class that we teach proofs, right? I mean, you're absolutely right. I'm an algebraist. I prove things in algebra all the time. But typically in an algebra class or in an algebra 2 class, facts about algebra are not proved, and we don't train the students to prove those facts. In calculus, we certainly don't train students to prove the facts of calculus. It's only in geometry class that we do that. But you're absolutely right that it's not clear that there's something intrinsic or inherent that makes it have to be that way. I think it's partly historically contingent, like a lot of things about education.
That's true. I just want to remind everybody that you should write your questions in the question and answer section, and you can go to it. It's at the bottom of the screen. I've got another question here. Isn't it this is from Thomas Klein. Isn't it ironic, though, that space ultimately is non-Euclidean? That is, we can work out geometry ourselves, but it actually doesn't strictly apply to our real world. So in a sense, the truth of Euclidean geometry is unreal.
Oh, well, thereby hangs a tale, my friend. I mean, in fact, I write a lot about this in the book. And in fact, the very quote from Poincaré that I just read to you, I use it in the following context because it's such a beautiful demonstration of what he was talking about, that people understood that logically there could be such a thing as non-Euclidean geometry well before there was relativity, right? Well before Einstein. This was in the middle of the 19th century. And so mathematicians were sort of saying, okay, our intuition tells us something about the way lines and points and circles work. But what if we kind of push our intuition to one side for a minute and really try to sort of proceed to extend our intuition by pure logic to create systems that we can't even visualize? Well, okay, then later people were able to visualize them, but systems that are completely beyond our intuition, but which make sense, which are internally consistent, which logically work. And it would have been easy to say at the time, and I think some people did, like, this is some kind of sterile BS that you're doing just to like enjoy your own logical machinations. Well, guess what? It turned out that those alternate geometries actually described physics, like actually described the world. So, I mean, this is such a beautiful example of this kind of, what's the word I'm looking for? Like thesis, antithesis, synthesis. There's like a word for this.
Synthesis.
Yes. I mean, these two strains, the purely logical and the intuitive visual, that one may race ahead of the other, but they're yoked together, and the one that races ahead will eventually pull the other along with it.
That's true. Well, thank you. That was great, Jordan.